Dear student, we will discuss here today the MOS capacitor, which is very much important topic from the electronic devices, and it is a basic component to build the MOSFET. That means MOSFET is nothing, just the four-terminal device which is extension of the MOS capacitor. That means if you will introduce something in the MOS capacitor, you will get the MOSFET, or in the MOSFET if you will short circuit the drain and source, you will get again the MOS capacitor. That means firstly we will discuss how the MOS capacitor is working, and after that extension of the MOS capacitor. That means whenever you will introduce two more terminals to this MOS capacitor, you will get the MOSFET. That means if you are interested to learn the working principle of the MOSFET, definitely you have to understand the working principle of the capacitor. MOS capacitor. This is basically the metal oxide semiconductor. That means here you will never get any conduction from metal to semiconductor at low applied voltage across this. I'm not taking the high voltage supply across this, otherwise this oxide will break down. Okay, so this value of voltage, whatever you are applying across this, that will be at low field. This is the architecture of the MOS capacitor, metal, oxide and semiconductor. And here we are providing some voltage V. But to learn this working principle of this MOS capacitor, firstly we will draw the energy band diagram of this MOS capacitor without the application of any voltage. So, as we will draw here, it is our E naught, that means the energy level of the vacuum. And after that, this oxide, here I have metal which have the work function of Q into phi F or phi M. What is our work function of the metal? The energy difference between the vacuum and the Fermi level of the metal, and it will be constant always because the number of charge carriers in the metal is constant. That means that number is constant for each and every material. That is why the work function of the metal will be always constant. Okay, and here firstly I am taking P type of substrate. And if it is the P type substrate, that means here you will get the EC, EV, and here this will be EF or EC, EV, and this is EFI, and this is oxide. Why I am not discussing the energy band gap of the oxide? Because this is so wider. Now this is the energy band diagram without any interconnection. That means this is isolated MOS capacitor, and energy band diagram will be this. And you can see from here there is the work function difference between the metal and semiconductor. There is the work function difference between the metal and semiconductor. If I am saying that this is a Q into phi S, where this is a Fermi potential or work function of this semiconductor, and this phi M is a work function of the metal. So if I want to connect this by a short circuit, that means I am just doing the connection between the metal and semiconductor, the charge carrier will flow from metal to semiconductor, because here energy is higher than this. So charge carriers will flow from metal to semiconductor. That means the charge will flow from this short circuit path and it will accumulate towards this side. Okay, and as you are increasing this, what will happen here? Here you are increasing the number of charge carriers at this side, and as you will increase the number of charge carriers, this will go upside. And please make sure that here this Fermi level should not vary, because you are not getting any conduction from here to here. The total net current in this loop will be 0. So please, you have to make sure that this Fermi level should not change, because the Fermi level is the measure of the average energy to the semiconductor. And here you are not getting any current from this side to this side. That means equilibrium will be maintained for any particular voltage, whatever you are applying from here. And that is the beauty of the MOS capacitor. For any applied voltage, all the time you will get this MOS capacitor will be at equilibrium, because you will never get any charge carrier from this side to this side. That means you are getting this bending in the energy band diagram without the application of any voltage. Okay, and some non-idealities will also come here. During the fabrication process, a lot of charges can exist inside this oxide. During the manufacturing process, many oxide charges you can have. Yes or no? And those charges will be positive always because of Mg plus. This is the mobile ionic charges inside the oxide, and the problem with this type of impurity is it is soluble in SiO2. That means this particular fellow, Mg plus, can move easily inside this oxide, which will alter the electrical behavior of this particular MOS capacitor. Apart from this, trapped oxide charge, interface oxide charge, and various non-idealities will also come into the picture, which will affect the performance of this device, and which we will take one by one. That means the first assumption which we will take, that we will neglect the effect of this phi ms, or in other words, if it will also contribute here, this bending will be a little bit more. Okay, and if the bending is happening here, that means to again flatten this, we have to apply some external voltage to get again from this blue curve to black curve. Okay, that means here this phi ms as well as this oxide charge, it is positive. To overcome this, you have to apply the exact negative charge, and I am saying this is my minus phi OX. That means the same developed oxide potential because of this, which is a positive nature, you have to apply this in the reverse direction. And this is known as VFB. That means the flat band voltage. Because of these non-idealities, the first one is this. The work function difference, the metal and semiconductor, there is an energy band gap, and you are connecting from the outside. It may cause the charge carrier flow from metal to semiconductor, due to which the energy band will bend. The second thing is non-idealities in this particular oxide. Various positive charges will exist there, and you will get a lot of non-idealities factors. And we have to take care about those things. And I have taken that this is the voltage, external voltage which you have to apply to make this band flatter. That is the oxide charge inside this. And this phi ms is nothing, just the work function difference between the metal and semiconductor. Okay, in the ideal case, what will happen? This VFB will be 0 because you will neglect this oxide charge, as well as you will neglect the overall function difference between the metal and semiconductor. But if it is that is not ideal, you will take care about this. Okay, that means before starting the behavior of this, you have to add this voltage externally. Okay, so that means if you will apply this, then what will happen? This bending will bend out. Basically, this will be in opposite in nature, because here the phi ms is positive and as well as this QX is positive. That means overall number will be negative. This is at this condition. So if you will apply this particular voltage across this MOS, you will get again this, which is your ideal condition. If you will neglect those things, you will get this. But whenever you will take the work function difference as well as the oxide charges, the bending will occur without the application of any external voltage. To overcome those things, you have to apply this voltage to make this band diagram flat. That is why it is also known as flat band voltage. That means voltage required to apply across this MOS capacitor to get the flat bands. It is the meaning of the flat band voltage. Whenever you will take care about these oxide charges. Now, I am applying external voltage, and if it is my body terminal and this is my gate terminal, because you can control the conduction. Whenever you will go in detail of this, you will see by this terminal you can control the number of charge carriers here. That is why it is known as the gate control terminal. Okay, that means it will decide the amount of current. So this will become this and this will become this. So I am applying this voltage is VGB. The voltage between gate to body. And sometimes whenever you will start this in the MOSFETs with the source, you used to call this VGS also. Now this will come automatically. So I am for the first attempt I am neglecting this because this will create a problem. So I am assuming this is a flat case. And whenever I will discuss further things, I will introduce this flat band voltage separately. But what will happen if this VGS is less than 0? If this VGS is less than 0, means the electric field direction will be this. Because the potential will be like this. If this VGS is negative, that means the gate voltage will be at lower potential than the body terminal. So electric field direction will be this. If the electric field direction is upward, then the force on the holes of this and force on the electron of this, that means Fp is equals to Q into E, and Fn will be minus Q into E. Now, this is a vector quantity and this is also the vector quantity. Electric field direction is upward. So, this force on the holes will be in the upward direction. That means the whole of this will go upside and the force on the electron will be on downside. So, electron will move from this side. That means what will happen here? The hole will attract toward the surface and electron will repel down from the surface. In the resultant, you will get the whole crowd will be very high at this interface. But what is the beauty? You will never get the charge transfer from here to here. That is this hole cannot penetrate this oxide because it is an insulator. So all the holes will get accumulated across the surface. And this mode is known as the accumulation mode. Now, if I am assuming that this is the value of the psi s, that means the voltage developed in the accumulation of this, then always I will try to measure like this. Then electric field direction is this. Definitely the developed potential will be plus minus, because the lower potential electric field direction is this, means the potential will be plus minus, which is opposite to this. So I can say that for this VGS is less than 0, the psi s should be less than 0. Where this psi s is nothing, just the surface potential. What is happening with the charge carriers across this particular junction? Because all the time, whenever you will go in the detail of the MOSFETs, all the conduction parameters are just because of these charges. So I am not interested in the entire bulk. I am interested only what is happening across this junction. What is happening at the interface of the oxide and semiconductor. Because the entire electrical behavior of this particular device will be decided by that only. That means the first case, accumulation. It is a p-type substrate. You are increasing the same type of charge carriers near the surface. That is why it is known as the accumulation mode. You are accumulating same type of charge carriers at the interface. Now, that means you are, in other words, we can say this, if the same type of charge carrier is increasing here, that means you are making this region more p-type than the bulk. More p-type means the Fermi level difference between the EF and EV. The energy difference between the EF and EV will keep on decreasing. That means what will happen? This will go in the upward direction. This will also go in the upward direction, and this will also go in the upward direction, and the energy band diagram will be this. But please make sure there should not be any difference in the EF. This will be always flat because you are not getting the overall current. These holes are not moving here. So this is a key point why the MOS capacitor is so much popular. Here you will get all the time the equilibrium condition. You will never get any current from here to here. And this is again the assumption. Any leakage is not here in the oxide. We are assuming this. And these leakages will not affect at the lower voltages. That is why I have started a journey from this. That this VGS value should be very less. So this is the first case, accumulation region. Whenever this VGS for p-type substrate, whenever the VGS will be less than 0, the electric field direction will be this. Hole will get attracted towards the surface and the electron will get rippled down from the surface. This is the reason. In the second case, again I will come to the flattened position. Now my second case is when my VGS is greater than 0. Now, if my VGS is greater than 0, means this will be at higher potential than this, so electric field direction will be in the downward side. Now, that means electric field direction will be in the downward side, and if the electric field is in downward side, it will ripple down the holes from the surface and it will attract the electron from this with the same relation. The hole will move in the direction of the electric field and electron will move in the opposite direction of the electric field. And electric field direction is downwards, so hole will get rippled down from the surface and electron will get attracted from the surface. But this will happen after a long time. What will happen initially? Whatever the electric field you are getting from here, you have some ionic charges also, because this is the acceptor type dopants, p-type substrate. So what will, those are also negative charged ions. So electric field, whenever the electric field strength will be low, what will happen? These electric field line get terminated on the negative ions. So you will get this. These are the cations. But if you will further increase this electron, free electrons are coming towards this. Because you know, always electric field will get terminated toward the negative charges, whether that is a fixed or mobile. Okay, and in this particular substrate, you have two types of negative charge carriers. The first one is acceptor negative ions, and the second one is free electrons. Okay, so the electric field direction is downwards. The starting electric field will get terminated toward the ions, and further if you will increase the electric field, these electrons will get altered here, and you will get one sheet of the charge carriers here near the surface. These red are my electron which are free, but you had trapped those charges between the insulator and the fixed ions. And you know one thing, whenever the ion will fix or any charge which cannot move, that will carry some potential. That will carry some potential, or in other words, that will carry some capacitance also, if any charge is not moving from its position. That is why you have studied that in the p-n junction, at this depletion region, you are storing the positive and negative charges, which are immobile charges, which cannot move. That is why you are getting the capacitance in the depletion region. The same type of things will happen here, but additional to that, you have trapped these charges near the interface, and these are the mobile charge carriers. Whenever you will provide any connection between them, which is MOSFET extension of this, whenever you will provide the interconnection here and here, and according to the battery, these charge carriers, red one, because they are mobile charge carriers, free electrons which can move. But here you don't have these options. So this will be the clear-cut scenario. What is happening? The substrate is P. With the electric field, as you will keep on increasing the electric field, the number of electrons from the surface, from the substrate, will keep on going the upward direction, and here the crowd will be keep on increasing with the increment of this VGS. As you will increase the strength of the electric field, more and more electron will come towards the surface. Okay, and this is the meaning of the inversion. In the bulk you have the holes, at the surface you have the more of electrons. Okay, so this is basically the inversion. And in inversion, a lot of people are interested because that will decide the working phenomena of the device. So this will break in several parts, not with respect to this. We know one thing. All the time what will happen? This psi s, direction is this, that means at this time this psi s will become positive. Positive to negative. The psi s will be in this direction because the potential developed will be this. So surface potential for this will be greater than 0 for this particular case. In the inversion, entire inversion I am keep on increasing. So whenever the VGS will be 0, this psi s can be anything. So from now onwards I am not interested in this voltage, because this will tell only the terminal characteristic, what is happening outside the device. What is the effect of this VGS inside the device we will see now. And here inside the device you have this psi s, surface potential. So whatever the things we will discuss after this, just because of the surface potential. What is the effect of this VGS in this psi s? And after getting the meaning, physical phenomena in the psi s here, we will try to develop the relation of this VGS and all the potentials here. Now, one thing we have studied, psi 1,2 is equals to Vt ln N1 by N2. We have studied this, where this psi 1,2 is a surface potential psi s. So we can tell this N1 is equals to N2 e raised to psi s upon Vt, where Vt is a thermal equivalent voltage. Where this my N1 is N surface, N2 is my N bulk, and this will become e raised to psi s by Vt. When the psi s is keep on increasing, that means the psi s value is positive, what will happen here? You know, the negative charge or charge carrier will come here slowly. That means at this surface, what will happen? This interface is this interface here in the energy band diagram. This interface. As the psi s value is greater than 0 but very less value, then what will happen? You are decreasing the hole concentration here, or you can say this, you are making less p-type at the interface. Because if the electrons are increasing means the holes are decreasing, and if the holes are decreasing means the substrate at the interface is becoming less p-type. If the semiconductor is becoming less p-type means here the separation will be here. The separation will be less. Yes or no? So what will happen? This will this will happen. Not this. The EF will not vary. Only this separation between the EFI and EF will keep on decreasing. As you will keep on increasing, that means at the surface you are making less p-type. That is why the difference between the EF and EV is keep on increasing. Or in other words, the difference between the EFI and EF is keep on decreasing. And here, the difference between the EF and EV is keep on increasing. Because you are making the surface less p-type. Okay, less p-type means this gap should keep on increasing, and this gap should be keep on decreasing. This bend or this band, wherever, because this band is equal to this band is equal to this band, and this is Q into psi S. Surface potential, whatever the potential you will develop here, that much bend you will get here. Okay? What will happen if the psi S is equals to phi F? Where this phi F is nothing, the Fermi potential, the difference between EF and EFI. That means if you will keep on increasing the bending of this, when the banding will become like this. That means this banding will be something like this. Whenever this banding will keep on increasing and come up to here, this, and you will know this value is Q into phi F, Fermi potential of this. Okay, and you know the Fermi potential is Vt ln Na upon Ni, and this is the Boltzmann relation basically, and I hope you have studied this in the junction theory, p-type and n-type materials. Whenever you will make the junction, you will get such type of Fermi potentials. Now what will happen if you will keep on increasing the VGS, and if you will keep on increasing the VGS, this psi S will keep on increasing, and if this psi S is large enough, is equals to phi F, then what will happen here? Then calculate the N surface, that means the number of electrons at the surface, where number of electron at the bulk is minority concentration of here. So N bulk is Ni square upon Na, and e raised to psi S value is this, because you have decided that the psi S value is equals to phi F. Then you will get Vt ln Na upon Ni divided by Vt. Then Vt and Vt will cancel out. You will get Ni square upon Na into Na upon Ni. This will cancel out, this will cancel out, the number will become Ni. At psi S is equals to phi F. What is the meaning of this? From p-type substrate, you have made the intrinsic type. That means the whole concentration are decreasing. Yes or no? Because you have decreased the whole concentration from Na to Ni, and you have increased the electrons concentration from Ni square upon Na to Ni. Then only you will get the multiplication of both the charge carrier will be Ni square, mass action law. And why you can apply this? Because you have assumed that any charge is not transferring from here to here. Because the mass action law is only valid for the equilibrium condition. Okay. That means at this particular surface, this is Ni. Before this, what is happening? You are depleting the holes from here. So, whenever the psi S is increasing from 0, flat band condition, to phi F, that is known as the depletion mode. That means when the psi S is less than phi F, but greater than 0, this is a flat band condition. This is the case where the entire holes will be equal to the number of electrons, because you are keep on increasing the electron concentration at the surface. So this particular region, when the psi s is, this region from 0 to phi f is known as depletion. Because you have depleted the hole from here, which was the majority charge carriers for p-type substrate. You have deplete the holes from the surface. Now, if you will further increase this VGS, further increment in the psi s you will get, and assume that this psi s will become 2 phi f. If this psi s will become 2 phi f, then you will get square here. Okay, and this will become square. This will also become square, and you will get here Na. But what is happening here if you will keep on increasing this? It is N surface. N surface goes to Ni previously, but now the number is becoming Na. What is the doping concentration here? Na holes. But what is happening at this particular voltage? Psi s goes to 2 phi f. Here, the electrons is equal to the doping concentration of this. That means Na, number of electrons you are having at the interface. What is the beauty? Previously the hole was Na here, now electrons are Na here. That means you have inverted the behavior of this surface, interface. Okay, that is the meaning of the charge inversion. So, whenever you are increasing the value of the psi s from phi f to 2 phi f, but the number of charges are less. So, you are saying that this region is nothing, the weak inversion region. Because you have inverted the channel, but the number is very poor. So weak inversion. The number is increasing but very less amount in the opposite type of polarities. Okay. Effective number you will get at this particular point. Psi s goes to 2 phi f. And that is also known as onset of strong inversion. Onset of strong inversion. That means from there you will get the significant meaning of the opposite type of charges. What we have discussed till now, when psi s is less than 0, accumulation. When psi s is greater than 0 but less than phi f, this is a depletion. When psi s is between the psi s and 2 phi f, this is a weak inversion, because you have inverted the channel but the number of charge carriers in the inversion region is very less. This is psi s is equals to 2 phi f. This is important. This is onset of inversion. That means from where you can see the significant change in the charge carriers of the opposite side. So this is my important point. And after this, the crowd here will be more. And if you want to justify, you can take the number psi s equals to 2 phi f plus 6 phi t. Phi t is nothing, just a Vt, thermal equivalent voltage. And you will see at this point the N surface will become 400 times of Na. Here the bulk have the whole concentration of Na, but at this side the electron concentration will be 400 times of Na. That means here the number of electron doping is much higher than the whole concentration at the bulk. That is the meaning of the strong inversion. But we know one thing, for capacitance, only immobile charge carriers are responsible. So, whenever you will discuss about these mobile charge carriers, that will never participate in the capacitance. Again, it is an assumption. Okay. That means I will take the assumption, whenever I will take this into account, I will assume that these are trapped between these oxide and this insulated layer. Then only you can take the capacitance of these also. But if for lower voltages, if these are not there, you can neglect them. Because for lower potentials, these numbers will not come into the picture. Now, if we are trying to manage this also, how much voltage you have to apply to get the inversion? This is VFB. That means now we will take care about the non-ideality also. So, here the value is psi OX, the voltage across the oxide, and voltage across this psi S. So, the total number, whenever you will write down from here, you will get VGS is equals to VFB plus psi OX plus psi S. I have taken all the voltage drops, and again I have taken one assumption. There is not any potential difference between this contact and this contact. This assumption you have to assume. If the metal will be same, and if this metal and this metal and this metal and this semiconductor are same, there will not be any contact potential across this. Same as in diode. There will be a 0.7, but from whenever you will connect from the outside of that, you will not get anything. Same type of assumption we have taken here, then we will get this. VGS equals to psi OX plus psi S plus VFB. Okay, if you will take the ideal conditions, this will be 0. Up to here, we have discussed. Now this psi OX, we have to take into the account what is the effect of these things. Now, if any charge transformation is not here, means the charge neutrality must have to be followed. Otherwise, you will get some voltage here. Yes or no? And the current also. But if this total energy charge conservation will come into the picture, total charge inside this must have to be 0. Otherwise, the charge conservation will violate. So, here I am saying the QG, here QOX, and here the QB, bulk charges, or CD, or QD, whatever the depletion region charges, whatever you want to call here. I will take as a QB, means bulk charges, because this is, previously it was the bulk. At later it will convert into channel. Okay. So, the total charge is QG plus QOX plus QB is equals to 0. If it is, assumption what we have taken here, the charge conservation. And these charges are per unit area. So you not have to think that it is a total charges here. Per unit area. Whenever you will multiply with the area, you will get the total value. So, if we will neglect the effect of this QOX, then QG is equals to minus of QB. And in the QB you have two type of charge carriers, QB, QI plus QD, where D is the depletion region charge and the QI are inverted charge, that means inversion charges. This I for inversion charges, red color, and this depletion charges are nothing, these fixed ions. Okay, and this is a QG, which will vary across this. That means you will assume that here all the positive charges in the metal, and here you will get all the negative charges. And this is across this capacitor. Yes or no? If I want to tell the charge across this capacitor here, QOX will become minus of QB. Because here the charges are QB Yes or no? And here, across this only you are measuring all the charges. Across this. So, this will come into the picture. Okay. For lower potential, we will assume that this Qi will become 0. So, total number will become minus of Qd. Okay, just I will paste that value here. Q is equals to CV. That means the QOX is equals to COX into psi OX. Psi OX value will be QOX upon COX. So VFB plus psi S plus QOX divided by COX, and you have calculated that the QOX is nothing minus QD. And here you are getting the depletion region only in the single side. Yes or no? In the bulk only, you are not getting any depletion region here, and it will act as a single-sided junction. And if it will act as a single-sided junction, then the depletion region W dep in this side is equals to 2 epsilon by Q psi S, the voltage across this, upon NA, the doping or the bulk side. Now, if I am interested in this total charge, what will I do? These are the acceptor charges. So, minus QNA. This is the charge density in this side. And if you are interested in per unit charges, you will multiply by W dep. Then this will become QD. QD per unit charge. This is a volumetric charge density. You have multiplied by one dimension. That means this will become per unit area. So whenever you will multiply this, you will get the QD will become minus root over 2Q NA epsilon into psi S. Okay, as you will put that value here, you will get VGS is equals to VFB plus psi S plus. Because this minus and that minus will cancel out, you will get root over 2Q NA epsilon upon COX into root over psi S. And this constant value can be represented as gamma, and after that you will write down VGS is equals to VFB plus psi S plus gamma times of root over psi S. In these derivation, I am just trying to show you how you are getting the voltage expression. That means how you can estimate the effect of this voltage in the device. Now, you are interested how much voltage is required to get the sufficient amount of inversion charges here. And you have just recently studied that this is the point, psi S is equals to 2 phi F. And what is a phi F? 2 Vt ln Na upon Ni. Okay, now see, you know this, you know this, you know this. So, you will get the value of the psi S also. VFB are the non-idealities, that means definitely you will know. That means if you know this psi S, this, and in the gamma also, all the values are constants. That means if you are able to calculate only the work function of the material, of the bulk, you can estimate the voltage required to generate the number of charge carriers here. Sufficient amount of charge carriers across this. And whenever you will get psi S equals to 2 phi F, that is the meaning of strong inversion, onset of strong inversion. At least that much voltage is required to invert the channel. And that voltage of VGS is known as VT, threshold voltage, which you have studied many a times in the MOSFETs. VFB plus 2 phi F plus gamma times root over 2 phi f. This is the threshold voltage. And you can estimate from here. If this value are dependent on these parameters, this is known as the body coefficient. Gamma is known as body coefficient. This is known as the body coefficient. Now, the effect of various parameters of this device on the threshold voltage. If you will increase the NA, that means the doping of the substrate, this will increase. If this also epsilon upon into TOX. If you will increase the permittivity of this oxide, that means if you will use high K dielectric instead of the any low K dielectric, if you will increase this, automatically this VT will decrease. That means I am taking the relations. First one is doping. Na is increasing, then the VT will decrease. Second one, if the epsilon OX will increase, the VT will decrease. Third one, the oxide thickness. If you will increase this oxide thickness, then what will happen? The VT will keep on increasing. TOX is increasing, the VT will decrease. Yeah, these are the effect of the device parameters on the VT. And all the time you will try to reduce the values. Okay, all the time you want less voltage required to generate the opposite drive or charge carriers. So your always interest should be to decrease the value of the VT as much as possible. So to decrease this VT, what is required? You will decrease the value of the TOX. That means the doping of this body should be minimum. The oxide thickness should be minimum, as well as you have to use the high K dielectric. These are the important points for the MOS capacitor, and after that we will discuss about the capacitances. Now, this is the COX, and after that this is the total CB. You have stored the charges here at the bulk. So I am saying that this is QB. That means whatever the charges you have stored here and some charges you have stored here. This is the total CGB. That means from gate to bulk. In how many sites you can store this? Either here or here. What is this COX? If you are not applying anything here, that means if the VGB will be 0, then this will go to hell. Because these all charges will introduce only whenever the VGB will be greater than 0. Otherwise, what will happen? Either you will get hole, and hole will never participate in the capacitances. Because to get the capacitance, there should be ion or fixed charges. On that case, you will not get any ions in the accumulation region. So, whenever, firstly I am writing here, the CGB is equals to 1 upon COX plus 1 upon C. That is, if the capacitances are in series, this is a relation of the series capacitances. If this VG is equals to 0 or less than 0, all the times either you will not get any charge here or you will get the holes, accumulation reasons. That means if this is a VGS, below than this or at this, what will happen? Either you will not get anything, depletion, flatband, or you will get holes, accumulation reasons. And hole are mobile charge carriers, they will not contribute in the capacitances. That means only capacitor you will get across this oxide. So before this the total this much is a capacitance which you will get. And this is COX, oxide capacitance. But as you will keep on increasing the VGS value, this will also come into the picture. And if this will also come into the picture, whenever you will add them, you will get less number of total capacitance. And this number will become like this. And up to some extent until you are getting this. And if you will keep on increasing the voltage of VGS, the inversion charge will come. And if the inversion charges are coming in the picture, they will never contribute in the capacitances. But because to get the capacitance, only immobile charge carriers are responsible. So after some voltage you will get this. And at which voltage you will get huge number of inversion charges after VT. That means this value will keep on decreasing up to VT, thermal voltage. After this, the participation of these red color inversion charges will not affect the total capacitance. And this is known as the minimum capacitance offered by this, and this is the maximum capacitance offered by this. And this is the CGV, total capacitance. And this is a CV curve of MOS capacitor. And this is at high frequency. And it's all about the MOS capacitor.